Hi Roberto, I wanted to ask you, do you try to enter in the class with any other email ID? Ah, okay, so because I don't know, so that's why I never admit, but since today I got to know, then from the next time I will remember about that. No problem. Mhm, mhm. Okay. So don't worry, I got it. I will I will remember. So we know that U is going to be the initial data will be carry along the characteristic dx over dt equals to U. dx over U. So when x is less than 0, what is the initial data? 0. So what will be the solution? U equals to 0. U x comma t equals to 0 for x is less than or equals to 0. In the same way, since this is constant and it is going to be the initial, so u naught x will be coming 1. So that is going to be solution. So 1 for x is greater than alpha. Is it clear? Okay. Now we are very interested in the reason. We are very interested in the reason this one, because this is the reason where we need to compute the solution. This is the reason where we need to compute the solution. Now we are going to solve that. I already have uploaded the notes, so you may have a look at the notes, but don't worry about that. It is very easy. You guys are expert in solving this PDE. So dx over dt is going to be u naught of xi, and where u x comma t is going to be u naught of xi. The solution is going to be u naught xi, and xi will be coming like this. So x equals to xi plus t u naught of xi, or xi equals to x minus t u naught of xi. So in we are solving the problem in the range this. So x equals to xi plus t. What is the value of u naught xi in this range is x over alpha. That is, so basically xi over alpha, because we are using u naught xi. So x equals to xi 1 plus t over alpha. That is xi t plus alpha over alpha. So xi is going to be alpha x over alpha plus t. Now u equals to u naught xi, and what is the value of u naught xi? Xi over alpha. So xi over alpha. So solution is going to be x over alpha plus t in the region. So what will be the final solution? 0 when x is less than or equals to 0, x over alpha plus t when x is lying in the region, and 1 when x is greater than alpha plus t.
And what happens to the function between alpha and alpha plus t?
Sorry,
What happens to the function
I,
where
I am going to
when
tell you
we take?
that, but I am
Oh, okay.
to tell you.
Okay.
So this is the reason if t is greater than 0. So this will be the solution, because the solution is continuous. The solution is going to define in the whole region. So alpha to alpha plus t, because t is positive. So when x will approaching to alpha plus t from left, it will be coming 1, and when x is approaching to alpha plus t from the left, right, it is coming to be 1. So to make the solution continuous, this will be when x lying between 0 to alpha plus t, the solution will be this. Now let's see with the help of the characteristic. I should go to the next page. Let me go to the next page. I'm just copying, but I will remove it just to draw these things. Oops, sorry. I am very bad at copying. I don't know, every time I make a mistake. So let's draw. Can anyone check whether US and UT are continuous or not at x equals to t plus alpha? The derivative. Oops. Can you check? You are a real analysis student, so it might be easier for you.
Problem will be like that in the definition of the function between 0 and alpha plus t, there's where the fun.
So just tell me whether it is continuous or not, and then I will be proceeding. Then I am going to show you the graph.
The derivative with respect to x is just like it's a constant, right? It's 1 over alpha plus t, so that's a constant, and the function is constant. It is, well, 0, 1 over alpha plus t. Yeah, it makes a jump from
I can
0.
just don't discuss. Just tell me whether it is continuous or not, and then I will tell you why it is continuous and why it is not. Just tell me without it.
No. The function is not continuous.
Not continuous. Yeah.
The derivative. The derivative.
Mm-hmm. Yeah, tell
Yes.
me. You are going right, Camilo.
Yeah, I think the same. Both derivatives are nor are continuous.
Yeah, so and in this region, the derivative is coming to be 1 over alpha plus t. In this region, it is 0. So when you will be approaching from left and right, it is going to be 1 over alpha plus t, and it is going to be 0. So basically, left hand limit and right hand limit for both, like for t and for alpha, is not going to. Here we are not concerned with the t because t is taken to be 0. But for t positives, that is basically our concern. So for t positive, we will be taking the left and right limit from this place. So when you will be approaching, so it will be coming like alpha plus t square. Again, it will not be converging because this t will be x will be tending to alpha plus t from here, and here it will not converge. So that is the reason. I just because you need to be very careful with the thing that this is a weak solution. This is a weak solution, and in the case when we take a jump, then that gives the shock wave solution. So this is a weak solution. The solution is globally defined, but the derivative of the solution is not smooth. Is not it?
What do you mean? Okay. There's a weak it's a solution is a weak solution if the derivative is not continuous.
Yeah, the solution is defined. It globally exists, but the derivative of the solution is not continuous because.
But how do you define a weak solution? Like in general, In this
So
kind of problem,
the weak solution is defined in the compact sense, in the distribution sense. So we know that if U is belonging to the domain omega and omega is contained in R cross R plus. R cross R plus, because U has the component x comma t. So x is coming from the real number and t is coming from the positive real numbers.
yeah, time is just positive.
So when you will be taking this should be satisfying. You are taking the integration. Now to define the solution in the weak sense, we multiply a compact function phi and pass this derivative, and this derivative is passed with the help of the knowledge that this phi is a compact support. Compact support means the value of this function phi on the boundary of R plus and R is going to be 0. R plus and R, boundary of the R plus and R is going to be 0. So phi x comma t is defined, it is a compact support. So it is defined in such a way that phi minus infinity comma t is equals to phi infinity comma t, or you can simply write x limit, because writing minus infinity something vague, we cannot say that. X tends to minus infinity, and here limit x tends to plus infinity, it is 0. And also when we are at t, so phi of x comma 0 is equals to limit t tends to infinite phi of x comma t, that is 0. So on the boundary of the time, like that is basically our domain, and on the boundary of the real number minus infinity to plus infinity, this function phi has 0 value, and in the inside of the domain, this is infinitely time differentiable. The function phi is infinitely, so this phi is known as compact support. And when we operate phi and then put this integration, so the differentiation pass to the phi, using this condition we will expand the derivative. And so in that case, if this function u satisfy this condition, then we call that u is a weak solution of the given partial differential equation. So since u is continuous, since only the property of the u is continuity will be used here, because we are not talking about the shock solution, we are talking about the solution whose derivative is not defined, whose derivative is not continuous, but the solution itself is continuous. So when you will be approaching like whether u is solution or not, so you can see that ux comma 0 is going to give you the initial data. U x comma t is satisfying the function, but it is satisfying the piecewise. It is satisfying its piecewise, because ux cannot be defined at alpha plus t. So that is the reason why we define the weak solution of a hyperbolic PDE. So the solution is defined in the globally, but piecewise, not like not on a continuous domain. It is well defined. It exists, but it is defined piecewise.
That's why it's called weak solution,
Yeah.
because it's piecewise and it's maybe not continuous.
So it is not like it is not a smooth solution. Basically, that's why we call it weak solution. Smooth
Weak
means
solution,
the
okay.
derivative should also be continuous. Smoothness
Yes,
comes from that the derivative should also be continuous. So it is not smooth, it is a continuous solution, but it is not smooth. So that's why we call it weak solution.
perfect.
And
Thanks.
however, when comes the property that it has a sudden jump, In that case, we don't use this weak solution condition. In that case, we use the second definition of the weak solution. So you can see that I have given you two definitions of the weak solution. One which I use to derive the Rankine-Hugoniot jump condition. Here I write the given differential equation in the form of differential, and then I operate this operator. However, the second one was written like this. Do you remember that? So in that one, I took that even the solution is not continuous. I gave the two definition of the weak solution. Do you guys remember? No? Just wait. So I give the two definition of the weak solution. This here I am assuming that even U is not continuous. That's why firstly I am applying the integration operator basically, which is the basic form of the conservation law, and then I am operating the derivative, the rate of change of that integral value. And the second one, where U is piecewise continuous, I get this definition. Even the derivative is piecewise continuous, I get this definition. So here I am taking the another definition here, and this definition is used to derive the Rankine-Huguenot jump condition. Because the Rankine-Huguenot jump condition, it is assumed that the function has a sudden jump along a curve. Are you able to catch these things?
Yeah, and you can measure that jump.
Yeah, even we can.
You gave us a way to measure the jumpingness of the function.
Yeah, so with that jump, you will be able to write the solution before the discontinuity and after the discontinuity. The solution before the discontinuity and after the discontinuity is connected with the velocity of that discontinuity curve. So that was the Rankine-Huguenot jump condition. So here we can see that our solution U is continuous. It is greater than 0, but it is not smooth. And let's plot the graph, because the graph is going to give us how the solution is going to behave. So every time when we plot the graph plays a very important role, because it shows us how the solution is varying. So what was our initial data? Suppose this is your x line and we are taking t equals to 0, so u naught of x, and this is your u naught. Because t is 0, so we are not portraying the axis of t, because t is taken to be 0. So at x is less than or equals to 0, at x is less than or equals to 0, what was the initial data? U naught was 0. So if this is u naught and this is x axis, so at this the solution is going to be this line. Is not it? Again at t equals to 0, again at t equals to 0 and x is less than or equals to alpha. In that case, the initial data was this. Is not it? So this will be coming like this. So it's not it, and it will be going to 1. Okay, and the third condition was x is greater than alpha, u naught was 1. So again straight line parallel to x-axis. So this is the initial data which I am plotting. Now what will happen to the initial data when x is approaching to, when alpha tends to 0? What will happen to the initial data when alpha tends to 0? So when alpha tends to 0, this will elapse. This point will elapse. Is not it? Because here x
it will tend to infinity.
Just focus on the domain.
Okay.
X is less than or equals to 0, x is greater than alpha. So when alpha will tends to 0, this will elapse. There will be no concept of the interval 0 to alpha. Is not it? Is it clear? So we will be only in this when alpha tends to 0. We have value x is greater than or equals to 0. Sorry, x is less than or equals to 0. This will be fine. And the second interval was greater than 0, less than alpha, and greater than alpha. When alpha will approach to 0, this interval will elapse, and so we will not talk about that this is becoming infinity. So that is the thing which we are focusing here. That is the thing which we are focusing here. So greater than 0. Now, can you see that it has a sudden jump at x equals to 0? Can you see? So what is the initial data? Every time, please pay attention to the drawing. So this is x. At t equals to 0, this is u naught. So at x is less than or equals to 0, this, and at x greater than 0, at 0 it is 0, and x it has sudden jump. So that is the Riemann problem. Here it forms Riemann problem, the Burger equation with the Riemann problem. Basically, this equation ut plus u square over 2x equals to 0. This is the initial condition which has a discontinuity at x equals to 0. So a hyperbolic partial differential equation with this kind of initial condition is known as Riemann problem. Next, we have plotted the initial datum. What is our next aim? To plot the solution. If you guys have any small doubt, then please ask me. Next, we are going to plot the solution. So firstly, we will plot the solution. What will happen when this alpha tends to 0? Just write it simultaneously. The solution will be u x comma t 0, x is little. Here you can see that now t is appearing. So when alpha tends to 0, still this region will be here. So x over t and 1. So that was the main point how we are writing the solution. Is not it? So firstly, plot this characteristic, and then we are going to, if you will be able to plot this, then you will be able to plot this very easily. So let's plot. Now we are going to plot u along the line dx over dt, because we are going to plot the solution. Now t is not 0, t and x both are varying simultaneously. In this solution, t and x are both varying simultaneously. T is positive because t is time in the Burger equation, and x is going to take the negative to positive both value. So this is your x, and say this is your t-axis. Now tell me, at x is less than or equals to 0, what is your solution? 0. U equals to 0. Is not it? So at this dx over dt equals to u, and at what angle, this is 0, at what angle tan is infinite? This is basically, this is going to be the slope.
90 degrees.
90 degree. So how will be the characteristic will be coming? The 90 degree, it means the perpendicular.
Yes.
Every plotting has some specification, but you need to be very careful from the first class how I am saying dt over dx is equal to the slope of those lines. If you remember, so this is u equals to 0, that is coming to x is less than or equals to 0. Now the second condition comes when x is greater than alpha. Suppose this is alpha. In that case, dt over dx is going to be 1. So what will be the slope? 45 degree. Sine 45 upon cos 45. Is it clear? So tan is 1 when theta is 45 degree. It means, please draw a very smooth curve, because I am drawing very bad curve here, but it just convey the message what I want to say.
I'm not getting the part where you look at the function and then you are plotting the angle that corresponds to the tangent.
Okay, so if I told told you that if we have this partial differential equation, then along the characteristic dx over dt equals to u, the solution is going to be constant, and that constant comes in the form of initial data xi and becomes u naught xi. So this curve is plotting x versus t, and if just remember your schooling that if we are drawing any curve x versus y, so what is the slope of those curve? dy over dx, that is our real analysis. So if I am plotting x versus t, so what will be the slope of that curve? dt over dx, because here y is t, is not it? Y is t axis. So the slope of the curve is going to be dt over dx. And how that dt over dx will be encountered? That dt over dx will be encountered by looking at the solution, because dt over dx is u naught, and u naught is 0 when x is less than or equals to 0. That is 1 when x is greater than alpha plus t. So at t equals to 0, it is x equals to alpha. Are you getting my point? Is it conveyed? If you
Yes.
have small doubt, then please do ask, because this is the most important part of the calculation. You can do the calculation anytime, but this geometry should be very clear. So this is next, we are left with x over alpha plus t when x is lying between 0 to alpha plus t. So at alpha equals to 0, this is x over t, and when it is increasing, so it will be increasing, like you can plot, it will be increasing, like now we have different slope, but they will not intersect because they are expanding in the region, they are not intersecting.
I have a doubt about the u equal to 0 angle that forms that slope. When you have like when the slope is 0, then you have the angle 0, right?
dt, that's what I was told you. Now
Yeah.
that what is the mistake you are doing? Let me tell you. Here I say that if I am plotting any curve y in function of x, then dy over dx is the slope. So if I am plotting x versus t, so what will be the slope for this? dt over dx, is it clear or not?
Yes.
And the characteristic was dx over dt. So to write the slope, I need to write this function 1 over dx over dt. And that's why when dx over dt is 0, then it becomes 1 over 0. That is infinite.
Okay. Yeah. Sorry.
So the infinite is the angle sine theta over cos theta. Cos is 90, it's infinite. So tan is infinite. So the straight line will be the straight line parallel to the t-axis. In the same way, now in this region it will start like this. This region is very important. Now in this region the slope is going to vary like this. So it will be, the theta will be increasing, because we know that between 0 to 1 the theta is increasing. So in this region the slope will be like this. It will start from 49 and then it will start to expand. And it will expand until it becomes parallel to t-axis, but it will never intersect, because in this case the curve is not intersecting. So please plot a pretty picture of this. My plotting is disaster. So I can show you. So this is the reason where the solution is u equals to x over alpha plus t. Now let's come to the point. What will be the case when alpha equals to 0? When alpha equals to 0. Is it clear? Do you guys have any doubt in this plotting? No? Okay. The second reason comes, suppose this is your figure A and say this is A naught. Say this is B naught, because this is the initial condition. Let's plot the figure B. Again, this is x-axis. This is t-axis. Here you need to pay little bit attention. So I said that alpha equals to 0. So x is greater than t. Alpha equals to 0. So this is 0. X is less than or equals to 0. So this is. So here this is going to be solution. U equals to 0. And in this region the solution is going to be like this. U equals to, all of this has 45 degree, all of this has 46 angle. In this region the solution will x over t. And it will expand until it becomes 90 degree. So what I told the definition, do you guys remember, if the rarefaction wave is expanding from a single point, there it is centered rarefaction wave. This is centered rarefaction wave, and this is expansion. Do you remember the definition? Let me tell you. So this is the centered simple wave and this is expansion wave. In the last class I explained that if the wave is emerging from a single point and it start to expand, then it is known as centered simple wave and this is expansion wave. So here we are getting both the solution. Is it clear? Totally? Okay. Now we are coming to the initial data where we are going to encounter a shock wave. Here we can see that the initial data was increasing. For the convex flux function, the initial data was increasing. So we are getting a rarefaction wave. We are getting a solution which exists for all the time, a continuous solution, not a smooth but continuous solution. Let's talk about the compression wave. This is the most important part, and your assignment third is based on this question only. I have already explained the traffic flow problem. Next, talk about the compression wave. I don't call it a shock wave. You can call it shock wave, but the term shock is categorized for a unique discontinuous solution. So to write the uniqueness of a discontinuous solution, we need to go through the entropy condition. So that's why I am writing it a compression wave or discontinuous wave. When I will write that entropy condition and then I will say it when it also satisfies the entropy condition, in that case we call it a shock wave. Okay, so I won't say that it is a shock wave, rather than I will say that it is a discontinuous wave, because saying it is a shock wave will be a vague statement without the entropy statement. Now again consider the Burger equation. Consider the Burger's equation with the initial data. This is our Burger equation. It plays a very important role, and this is the most simplest nonlinear equation. By studying this Burger equation, we are able to study the rarefaction, expansion wave, and the compression wave. Okay, so with the initial data, Burger equation. Would you please check this initial data is continuous or not?
Yeah, it's continuous.
It's continuous, na? Yeah. So this is a continuous initial data, and when alpha tends to 0, again alpha tends to 0, so this part will be neglected. In that case, it will not be continuous. Is not it? 1, 0, x is less than or equals to 0, x is greater. In that case, it will have a sudden jump. Now, this initial data is defined in such a way that the initial data is decreasing. The initial data is decreasing. Now we have a non-linear hyperbolic equation. We have a conservation law where the flux function is convex and the initial data is decreasing. So the solution will be smooth or not. So the solution is going to show up a discontinuity is solved. Can anyone solve this problem for me and tell me the solution? You only need to find out the solution in this reason. Can you guys solve it? Just do it. You have 8 minutes if you are not able to solve it because it is your practice. Always use u naught xi equals to 1 minus xi over alpha. And there is a very interesting thing about the domain, how we will define the relation between x and t. That is the thing which I would like to discuss. When once you get the solution in this reason, for this reason, then I would like to tell you how you need to write the definition for x and t because that plays a very important role.
I don't know if my answer is correct, but I got u is equals to alpha minus x, all of this upon alpha minus t.
Exactly. So this is the correct answer. X minus, like you can write in the same way. Now, when we will be writing the solution, we need to be very careful with the domain, the 1 and the 0, because this was the case when t was 0, and the second reason will be this. So just be careful. You can see that when this x will approaching to t, when x is approaching to t, so this will be 1. So x is less than or equals to t. Because we need to show the continuity at the breaking point. How I managed to write it here, alpha plus t. So, and when this x is approaching to alpha, when this x is approaching to alpha, this becomes 0. When x is approaching to alpha, this becomes 0, so it would be left hand limit to the right hand limit. And when x is approaching to t, it would be left hand limit to the right hand limit. So this is the region. Now, what the region we are left with? T, x, and t is less than alpha, 0.
Camilo,
Sorry?
Camilo used the method of characteristics.
In the same way how I solved the previous problem, Hannah? Is it? In the same way. This is in your notes, like you can follow your notes if you are unable to do here. I have explained it in the notes, so don't worry about that. But this is the reason. In the same way, how you will define this boundary, that is very important. So every time, every line has some meaning. Now tell me, when this x will approach to alpha and t will approach to alpha, what will happen? 0 upon 0 case will be encountered. When x will approach to alpha and t will approach to alpha, so 0 over 0 case will be encountered, and in that case the solution is going to be blow up. So the problematic point is alpha comma alpha. So let's draw this figure. And what will be the solution when alpha is tending to 0? 1, x is less than or equals to t. This is the very basic problem, and when we work on the higher, like when we work on the system of equation, it is not that much easy to write in this way. This was a single conservation, like scalar conservation now. So you see, x is equal to 0. No. Here we need to be careful. I will write this. Just wait here. First plot the first graph, and then we will come here how the solution will be written, and that will be written with the help of the rank time using your jump condition. So the initial data is defined at t equals to 0. So we are not going to plot it t versus x. Rather than we will plot it x versus u naught. So we can see that u naught is 1 for x is less than or equals to 0, and in this region, this is the slope will be like this and then 0. So here this is 1, and then this, and then this. So this line is u naught equals to 1 minus x over alpha, and this is your alpha. This is u naught equals to 0. This is u naught equals to 1. Next, plot the solution. Now the solution will be plotted in x versus t. Okay, so tell me, when x is less than or equals to t, then u of x comma t, u of x comma t is 1. So what will be dt over dx? 1. So what will be the slope? 45 degree. However, when x is greater than alpha, this is 0. So if suppose this is the alpha point, so this is going to be like a straight line, and this solution x is greater or equals to t, like before that x is less than or equals to t. So if this is x is negative, so for sure this is going to be less than t, because t is always positive. Here this is negative x and x is less than t. So this is always going to be, here it will be evaluating like this, and here it will be going like this. Here the slope is going to be 45 degree. Here the slope is going to be 90 degree. So they are going to intersect at some point. Is it clear? I think it is clear how we are plotting the graph. That's clear how we are plotting U, projecting U. So when the initial point at t, so this is slope is going to be like this, and this slope is going to be like this. So this is, again my plotting is very bad, so don't, you may plot a pretty picture. So this is u 0, and this is going to be u equals to 1. Now the middle region, this middle region is nothing but this solution. So this point is the point where they are encountering, that is alpha comma alpha. And this is the graph of, so this is the graph of u equals to x minus alpha over t minus alpha. Now if we suppose this, what is this, what will be this line? What will be this line? Suppose this is the line.
That has a slope of, I don't know, like 1.
X equals to t plus alpha by 2, but how? Tell me. This is very, I think you might be getting it. So at t equals to alpha, this is going to be x equals to alpha. This line is passing through the point alpha comma alpha. And dx over dt is u naught of x, and dx over dt is x minus alpha over t minus alpha. Would you please solve this? And then you are going to get the line. Basically this line is going to be, the slope of this line is going to be dx over dt equals to x minus alpha over t minus alpha. Is not it? This is u. So this value of u is along the characteristic dx over dt equals to u not x. Along this it is going to be constant fixed. So basically this is not the thing. Can you please solve this? And then you will be getting the same line. You will be using the condition at t equals to
Understanding.
Do you this understand dx over dt equals to u equals to constant? Is not it?
Yes, that's the method of characteristics.
T equals to this, along this characteristic x versus t, the value of u is this. So along dx over dt equals to x minus alpha over t minus alpha, the value u is going to be constant. The same thing which I explained in the method of characteristic. So you can solve this and can use the initial condition at t equals to alpha, x equals to alpha, because I am taking that line passing through this. At alpha, I am encountering a discontinuity. So you may solve and you will get the result. I am just telling, I just wanted to figure out your mind. I don't know how it is coming. Okay, so this, when you will be solving, because this is a single scalar conservation law. So every time you have ds over dt equals to u, and u is constant along this. I'm sorry. So when this alpha will collapse to 0, this will be the discontinuity line, this will be discontinuity line, and before this discontinuity line u equals to 1, and after this discontinuity line u equals to 0. Before x is less than or equals to t plus alpha by 2, u is 1. And after x is greater than t plus alpha by 2, u is 0. Is not it? So how I am writing the solution? This point is clear or not? How I am writing x equals to t plus alpha by 2? So I am saying that I am writing this exact line. I am saying that alpha comma alpha, the curve u equals to 1 and u equals to 0 is going to be coincide. So before this line, what is the solution? U equals to 1. And after this line, the solution is u equals to 0. So x is less than or equals to t plus alpha by 2. The solution is 1 and x is greater than t plus alpha by 2. This is already 0 and this is the solution when alpha will approach to 0. Or you can say that not alpha will approach to 0, t is greater than or equals to alpha, because here I did not give the condition what will be the value when t is greater than or equals to alpha. I only gave this condition because if I am writing this condition, so we were not going to get the solution. When t is greater than or equals to alpha, I did not mention here. So I am not saying t alpha is approaching to 0. I would say that when t is greater than or equals to alpha here and here alpha equals to 0. Now, can you see that even when in the initial data I am taking alpha equals to 0, your solution is coming to be two part. One when t is lying between 0 to alpha and one when t is greater than or equals to alpha. It means you are getting two set of solutions.
Sorry, you can repeat how to build the solution u of x of
I am not taking alpha equals to 0 for the time being because alpha is playing an important role here. For the time being, yeah, please repeat your question now.
how you build the solution when later when you compute the line the line in the point of discontinuity, how you construct all the solution in that case when you
Again, can I repeat? Should I repeat it again? Okay.
yeah.
So this thing is clear. Only this thing. You have computed it. So let's proceed. I am proceeding with the same initial data. I am not changing the initial data because this is the important. I will change the initial data for the time later, but don't take alpha equals to 0. This is the initial data and I am getting the solution u of x comma t equals to 1, sorry, x minus alpha over t minus alpha, x minus alpha over t minus alpha and 0. Now to make the solution continuous, I need to take the when x is approaching to t, then it becomes 1. So x is less than or equals to t. When x is approaching to alpha, then it becomes 0. Is not it? So to make it satisfied with the left and right limit, because our aim is to make the solution smooth, to make the solution continuous. However, in the below region, like t is less than x is less than or equals to alpha, this. Now I haven't kept any condition on t. I haven't kept any condition. The condition on t is still left. Now this is t is 0 and less than alpha, because as soon as t will be approaching to alpha, your solution will blow up. You have given the region of x. X is varying, x is including all the values for alpha, less than alpha, greater than alpha. But for t, I need to be very specific because at t equals to alpha and when this x is approaching to alpha, the solution will blow up. So I need to give two regions. In the case when t is greater than or equals to alpha and when t is less than alpha. So how I will be deriving that condition? So I will derive that condition with the help of the graph, with the help of the characteristic. So how it works? Can we plot this when t is less than alpha? So this is your t axis and this is your x axis. Suppose
That's the domain of the function, right?
so, this is alpha. And this is alpha comma alpha, the first point, the first critical point where the solution is blow up. Now you can see that this is the solution u equals to 0, and here all the characteristic collapse. This is the solution u equals to x minus alpha over t minus alpha. Now you can see that when this will collapse and you draw the graph that pass through alpha comma alpha, the curve x equals to function of t, the curve where it goes. Now the solution will be either 1 or 0 unless until again they did not collapse. But here we only have the one collapse point. We only have the one collapse point. So after this point, the solution is going to be 1 or 0. So we have two cases. The one case when t is less than alpha and the other case when t is greater than or equals to alpha. So in the case t is greater than or equals to alpha, the solution will be either 1 or 0. This region will not be coming. Now how that region will be computed? How you will define what will be that line? Before that the solution is 1 and after that the solution is 0. So we know that the line is going to be ds over dt equals to u, that is x minus alpha over t minus alpha. And how you will, when you will solve this differential equation, you will be getting a constant. So here I am saying that the line is passing through alpha comma alpha. So at t equals to alpha, x equals to alpha. So when you will use this condition, you will get the line x equals to t plus alpha by 2. It means before that line the solution is going to be 1. And after that line the solution is going to be 0 for the case t is greater than or equals to alpha. Now you can ask me why I am keeping one equality here. So you can keep equality in the both case. I am keeping this inequality on the basis of the initial condition x is less than or equals to 0, x is greater than alpha. And the condition is t is greater than or equals to alpha. So this was the case when alpha is not equals to 0, but still you have two set of solution. Still you have two set of solution, and they are collapsing. They are collapsing. It means the continuous solution is overdetermined. The continuous solution is overdetermined. You are not able to find even continuous solution. It has a jump. It has a jump along this line. What will happen when alpha will tends to 0? When alpha will tends to 0, the initial datum will be this that has a jump, and when alpha will tends to 0, you don't need to consider this case, because the time is always positive and you will be only stuck at this case. So u x comma t when alpha tends to 0 is 1, 0, x is less than or equals to t by 2 and x is greater than t by 2. So this is the solution. Is it clear now? Okay. So this is the solution. Again you can see that the solution has a sudden jump. Oops, I am making some mistake. Oh yeah. So x is less than or equals to just wait. I am making a mistake here. Alpha tends to 0. No, that's fine, yeah. I went to the another problem and I was seeing how it could be possible. So that is fine, yeah. So this is the case. And in that case, you will be plotting the solution like this. This is x and this is t, and this is the line x equals to t by 2. At this line, all this, sorry, because this is the only line where they are encountering. So this. Before that, the solution is u equals to 1, and after that the solution is 0. Oops, sorry. So the solution will be like this. There will be no reason where the solution is defined something else. Either solution is 1 or 0 and they are going to encounter, and this is the first point alpha comma alpha. So is it clear? Now, this was the rarefaction and compression wave. We are going to come to the shock wave in the next class because this was the case where you are encountering two solutions. Now, how you will define that the solution is unique? How you will be encounter the unique solution? The existence of the solution is fine, but our aim is to find the uniqueness of the solution. So we will be defining the lax entropy condition, and tomorrow we will define that lax entropy condition, and then I will define that. Then the discontinuous solution which is satisfying the lax entropy condition as well, that compression wave will be known as shock wave. So tomorrow I will be discussing that. For the time being, please read this thing wholly, and I think I haven't prepared a very, like I have solved, but I haven't drawn the graph in the. Do you guys need another notes for this, or this will work?
Where can we see like more of this theory in a book?
There is nothing like this is the very basic thing. You can follow the Lawrence Evans book, but the thing is that this geometry I am taking from the G.B. Vidan book. Let me write the name of the book. Actually, this is the research problem. This is basically we study in our PhD coursework. So let me write the name of the book, G.B. Vidan. Non-linear waves by G.B. Vidan. Oops, sorry.
Yeah, the part I'm not getting, it's like the plotting of the plotting part of all of this. Like I can define the straight lines in the domain, but the analysis of where it exists and the intersection of solutions and overdetermined things, I'm not getting a lot of like the geometry of all this.
Just wait. I would suggest you don't need to read the book because this is something PhD level book. What I have explained, that is the very basic. Just go through the notes which I explained, go through the problem which I explained today, and today go through the problem. Again, if you are not able to understand, then please tell me tomorrow in the beginning of the class. I will again explain the same thing. Because this geometry is very I don't think that if I will, like for me, Camilo, did you get all the point?
Yeah.
So I think you just need to revise. You just revise this thing again. If you are not getting, so tomorrow we can go over that again, because this is a very interesting part, and I think it is little bit difficult to capture. But once you capture this thing, it becomes very easy. Because you can see that I was encountering the minimum of that TC. So that was the first critical time. So how I encountered the first critical time alpha comma alpha. So that is the point. Just go through this, and that was the thing which I was telling. Always try to remember the previous thing, because the slope is coming from the previous class, and I explained more than 3 times how I was plotting the slope and how it was intersecting, because that was the main thing. If you skip that part, then it will be difficult to grasp this part. So please go through that part and then study, and then also try to solve the traffic flow problem. In the beginning of that today class, I explained the traffic flow problem. So try to solve the traffic flow problem which I have given in assignment, and this problem try to revise. Tomorrow we can again discuss, and then tomorrow I am going to discuss the entropy condition. By the end of this week, I am finishing this unit.
Okay.
Yeah, if you have any doubt, so tomorrow we can discuss about